Hello, I'm going to be going over design for sheet metal fabrication. I'm going to include an overview of die profile sheet metal fabrication operations, do a little bit of a rough cost estimate for die production, and then also touch on some guidelines for design for sheet metal fabrication. The main reference here is Boothroyd and Dewhurst, product design for manufacture and assembly. So parts can be made from sheet metal in two fundamentally different ways. The first is with dedicated dies that form and punch out parts from blanks. This GIF on the left, you can see an example of this where a strip of blank sheet metal is being pushed through and the die is bending as well as cutting off the part, which is then ejected, and the next part can be pushed forward into place, and the process is repeated over and over. On the right side, you can see an example of the other type, which is CNC punching machines, in which case these would need to take advantage of secondary bending operations through a brake press or something else of the nature. But you can see this is more typical of your CNC operations with an XY axis that moves the sheet metal around, and then a tool with different punches can cut out the parts and put different profiles onto the sheet. I will be focusing in this presentation more on the dedicated dies from blanks. So before I get too deep into the process, let's talk about the types of materials and thicknesses that qualify for sheet metal manufacture. Almost all of sheet metal manufacture is typically done with these materials: steels, aluminum alloys, copper alloys, and titanium alloys. These materials account for the vast majority of sheet metal manufacture. Steels can go anywhere from a 28 gauge up to 6 gauge. This would be 0.38 millimeters. To a little over 5 millimeters. Aluminum alloys, copper alloys, and titanium alloys, these tend to be measured more in nominal thicknesses of a similar range. If you go thinner than any of these ranges, these no longer qualify as sheet metal, and they tend to fall more into the category of foils. And thicker than this, we would treat it as plate, where you do other manufacturing processes. So these are the typical materials you're looking at when considering this manufacturing method. In addition to the thickness of these materials, you also want to consider some key material properties for sheet metal manufacture. These include cost of the material, scrap value, density, ultimate tensile strength, elastic modulus, and maximum tensile strain. Looking at this chart, it's worth noting that steel is a very, very good material for these processes. Not only does it outshine most of the other materials in the strength categories of elastic modulus and ultimate tensile strength, its cost is substantially less than most of these other materials. High-end titanium gives it a run for its money in ultimate tensile strength. And aluminum and titanium both outshine in terms of density, but for most applications, steel is going to be the material of choice, especially if you think about car and automotive processes or enclosures like computer cases and whatnot. The aluminum and titanium really get used more where strength to weight ratio is important, and you start thinking about aircraft or spacecraft where the costs are worth it. But otherwise, you'll see a lot of steel used in sheet metal manufacture. So let's talk a little bit about the process of individual dies for profile shearing. Here on the left, you can see a die press where you have a top plate and a bottom plate that are able to move relative to each other using some rails. Two main styles of die are the cutoff die and the part-off die. So the cutoff die here, you can see at the top and the bottom sort of shear off one part at a time, and so every action of the die will cut off another part. You can see on the right side there an important feature for these types of parts is that they sort of nest within each other, where the leading edge of one part and the trailing edge of the other part have an identical profile. And so this only works for parts like this. And when we get to design for manufacturability with this style of manufacture, you will look for opportunities like that where your two profiles are identical, your front and leading edge. The part-off die below is similar, except that it makes two cuts with every operation, both cutting the front edge of one piece as well as the trailing edge of the previous piece. And so what ends up happening is every punch of the die produces a part as well as ejects the scrap out the bottom that is found between the two parts. So in this way, you can avoid having to have the front leading profile identical to each other. This does lead to increased amounts of scrap, as you can't just butt the parts right up next to each other. There needs to be a thickness, the thickness of the material. There needs to be about twice that between parts, and it can also lead to slightly different edges in the two surfaces, which you might need to take care of with post-processing and deburring. But it allows you to have more diverse parts. Two other forms of dies worth mentioning are the blanking die and the cutoff and drop through. The blanking die allows you to have any profile perimeter you want. It cuts out the entire part. The drawback here is that there's a lot of wasted scrap, as this requires extra material between parts as well as around the part. So it is not as efficient. For the cutoff and drop through, it is actually an improvement over the previous method. It requires you to design parts so that they are symmetrical when flipped across the center line axis. This way, instead of cutting off one part and having a scrap fall through, it cuts off one part, and then the scrap is actually, what would have been the scrap is actually an additional part. So the part that drops through is another part. They're mirror images of each other, but you can just flip them and then post-process finish them identically. So those are two other methods that can be used. I'm not going to get super deep into the costs of shearing dies, but to give you sort of an overview of what factors influence the cost. First of all, the cost of the die. Through empirical testing, formulas have been found. This one, the cost of the die is 120 plus 0.36 AU. AU is the usable area of the die. So, depending on the larger your part, the larger the cost of the die, and it follows this relationship. To manufacture them, you can simply take that cost of die equation and assuming $40 per hour is what you would pay, you can figure out the manufacturing time there to be following the relationship of 3 plus 0.009 AU. So the costs and manufacture time of the die is just found through experimental empirical testing to be related to the usable area. Now we're looking at the cost of putting the tooling onto that die. It really depends on the profile complexity. Profile complexity XP really depends on two main factors. The first is the perimeter length to be sheared. So that is, you follow the length of that perimeter. And then the other one is the area of that smallest rectangle that would surround the punch in terms of your length and your width. And it follows the equation shown there. Now, taking that value and turning it into manufacturing hours, taking complexity and turning it into manufacturing hours, depends on, once again, some empirical testing and relationships have been found. 28 plus 1.03 times the profile complexity. And then there is a die type factor, FD. So we talked about the different types of dies. A blanking die, you just multiply it by 1. For a part-off die, you can multiply it by 0.91. And for a cutoff die, it's 0.88. So the time to produce those die tooling goes down with those types of manufacturing methods. So your overall cost of die tooling is really going to depend on the total die manufacture time. It depends on MPO, which is what we calculated in the previous slide, as well as MDS, previous calculated. And then it gets multiplied by a couple factors depending on the material and size and things like that. So you have FD, which is your die type factor, whether it was a part off or a cutoff. The plan area correction factor is FW1W, and then the die plate thickness correction factor, where you have to account for thicker die plates for certain materials and thicknesses, FP. And all those values of F have been determined empirically and can be looked up in tables found in Boothroyd and Dewhurst. Your total cost for die manufacture will be your MP times your cost of assuming $40 per hour. You would just multiply that by 40, or whatever current labor costs are. In addition to the cost of the die to be formed and made and tooled, we also need to worry about the cost of operating the press as well. We need to understand what size of press we're going to use, and that depends on a few different features of our part. So you can see here in this table, there are different single action presses that vary by bed size, which you need to make sure you pick a press that has a large enough bed size for your die. In addition, different presses have different press forces, and based off of that, they have different operating costs as well. So while rates vary, this is a chart from Boothroyd and Dewhurst that gives you an idea. So the force required for a part depends on the size of the part, as well as the material you're going to cut it from and the thickness of that material. And lastly, the length of the shear that will be necessary. So you can see that formula there at the bottom, F equals 0.5 U times H times L sub S kilonewtons. So to look at an example of this, we could say, for example, we want to cut some circular discs that are 30 centimeters in diameter from 12 gauge commercial quality low carbon steel. And so we want to select an appropriate press for that use. So we look at our formula, F equals 0.5 U times H times L sub S. And we'd have to look at the material specifically, in this case, low carbon steel, and go back and check the charts previously mentioned. The ultimate tensile strength of the steel is 330 times 10 to the third kilonewtons per square meter. The thickness of 12 gauge steel is 2.67 millimeters, or 2.67 times 10 to the negative third meters. And lastly, the length of the shear, it's just a circle, so we use the formula for the circumference of a circle, pi times diameter, in which case the diameter is 3 times 10 to the negative 2 meters. Multiplying these things together, we get a force of 415.2 kilonewtons. So if we go back and look at the previous chart, we're looking at the press forces here, and we need one with at least 415, so we have this 500 kilonewton press, which will cost us $76 per hour to operate. Now we do need to verify this press is big enough for our part, so it has a width of 80. Depth is not very relevant here because it's a flat disc, but a width of 80 centimeters would be plenty of a space for our 30 centimeter disc. And so the 500 kilonewton press, which has a large enough bed size, would be the appropriate choice for it. Now I'm going to go over some design rules for sheet metal fabrication. This is by no means a definitive list, but here are some of the highlights from Boothroyd and Dewhurst. The first is to design outer profiles with parallel straight edges defining the part width. This allows the parts to be manufactured more easily using cutoff and part-off methods, as well as the blanks coming off of a coil and just moving through the manufacturing process with less scrap and more efficiency. End profiles should meet straight edges at angles no less than 15 degrees. So on the left side here you see a part blank with semicircular ends, and though it is hard to cut off when those degrees approach zero angle with the edge, it is much better to cut off these semicircles with a larger radius that won't meet the edge so sharp, as in B. In general, when you're designing sheet metal parts, you want to avoid any narrow projections or notches. This would require weak sections in punches or die plates. You can see here those marked in A in the diagram would be narrow and would be pieces you want to avoid. All feature dimensions and feature spacing should be at least twice the thickness of the plate to allow proper holding as well as clean punches. Corner radii should also be twice the gauge thickness, and this will also help minimize corner stress concentrations. And then lastly, you can include relief cuts at the ends of bend lines that end at internal corners. So in this diagram here you can see D, there's an internal relief cut there, so when this part is bent at that corner, that that it bends cleanly and there's no stress concentrations. When you're lancing and forming bridges, you need to account for maximum tensile strain. You don't want to stretch the sheet metal beyond its failure point. This depends largely on the material, the angles, the lengths, but a good rule of thumb is that the length of the bridges should be greater than 4 times the height of the bridges. Often you'll see these flange holes to allow for sheet metal screws to make threads or bosses for things to align. You need to be aware of material ductility in these cases. If you have a punch diameter large D and you're using it to put a hole into to make a flange out of a smaller hole with diameter lowercase d, then the tensile strain follows this equation here. Tensile strain equals to the difference in the diameters divided by the large diameter. Obviously this depends on the materials, but typical heights of flanges will range between 2 and 3 times the thickness of the gauge of the sheet. So the choice of the thickness of gauge is affecting a lot of design considerations. Often you'll have a large sheet that you want to stiffen up by adding some sort of ribs or beads. You might see this with steel, like toolboxes and other things like that. You can see this on, truck beds and things like that as well. A rule of thumb is that the inside bend radius should be greater than or equal to twice the sheet thickness. If you make these ribs or beads have too sharp of corners, then you risk cracking or, weakening the material. The edges of circular holes, you definitely want to be aware of how close any of these types of features or slots will be to a bend. Often these punches happen after the bend, and being able to manufacture it too close to the bend is problematic. So once again, the general rule depends on the thickness of the material, and you would want to have a distance of at least 2 times the thickness of the material between the start of a bend and a feature such as these slots. And lastly, if you can design parts for cutoff or part-off dies, that is much more beneficial to how affordable the part is to be made. Also, if you can reduce scrap. So you can see here these designs on the right, they're all for a 3-hole bracket with the holes in the same relative location to each other, but the choice of the perimeter around those holes, in the first one, it's not a very efficient design. There's a lot of wasted scrap that's going to drive up your prices. In the middle one, the scrap is reduced, but they are not optimized for a cutoff or part-off method of manufacture. And in the last one, they'd be ready for a cutoff production, which would make it much more efficient and have far less wasted scrap. There is some interesting that pointed feature, but that is easily removed in the deburring process, which you'd probably have to post-process most of these anyways. So in summary, I've offered a brief description of the materials used in profile sheet metal manufacture, as well as some of the processes. We went over estimating die costs to make the die and the tooling that goes along with it, as well as the selection of an appropriate press and its operating costs. And lastly, we covered some design guidelines for sheet metal manufacture. There's a lot more details than this that go into different types of sheet metal manufacture, specifically bending or drawing out, that wasn't covered in here. So definitely go ahead and check out Bruthred and Dewhurst. It's a great resource for all of these. Thank you very much.